So, in the last class we were talking about how the involvement of water is absolutely essential for the concrete durability problems to happen, and the fact that most of the durability problems of concrete were interlinked with the permeability of the concrete. Okay. So, now permeability of concrete obviously depends on the porosity, and both these factors depend on the water to cement ratio of the concrete. We also discussed the fact that in concrete you can divide the section into two components. One is the cover concrete and the other is the hard concrete. The cover concrete is the one which is subjected to deterioration in case you do not have curing which is done properly for your concrete, and if you have any aggressive chemicals which are attacking your concrete from the external environment. So, the properties of the cover concrete to a large extent determine the overall durability of the concrete. Again, this is just depicted once more in this schematic diagram here of typical reinforced concrete. So, as indicated here, the cover concrete is what is subjected to the ingress of aggressive agents which involves chlorides, carbon dioxide or even water, and generally drying may happen at the surface. As we discussed earlier, it is difficult for water from more than 30 to 40 millimeters inside the concrete to really dry out of the concrete in normal drying conditions. So, you can imagine that it is the cover concrete which is primarily subjected to durability related problems, and for improving the characteristics of the cover concrete, it is within our interest to do curing as long as possible to ensure that cement hydration continues and the microstructure of cement develops in a proper manner. Okay. Now, in general, the problem of durability can be related primarily to the adequacy of protection offered to the steel by the concrete cover layer. Okay. So, the cover concrete holds the key to durability, and this is a concept that you will probably come across in most durability issues, and that is primarily because the cover concrete is the one which is protecting the steel from further corrosion. And why is the steel corrosion the primary characteristic which we need to worry about? Primarily because steel corrosion, unlike other durability problems in concrete, steel corrosion has the ability to reduce the overall load carrying capacity of the concrete structural member. All the other characteristics, all the other durability related problems of concrete generally tend to deteriorate surface characteristics of the concrete or maybe lower the surface hardness of the concrete, but they do not really have a great input towards the overall deterioration of the load carrying capacity of the member, whereas corrosion of the reinforcing steel can really take that to a new level. Okay. So, having talked about what is the primary reason for durability related problems in concrete, let us look at how we can divide durability and look at it from a different perspective. So, of course, you know that durability is composed of the concrete system and the aggressiveness of the environment. Now, we have to design concrete for a specific environment based upon the kind of physical and chemical deterioration mechanisms that are actually acting in that environment, right. The requirements for concrete mix design for a coastal environment is obviously different from the requirements for an inland environment, and we have to have some idea about how to do material selection in these conditions. So, based on that, we work out the requirements of the concrete system itself, which are composed of both materials that we use for making the concrete, including binder type, content of binder, the aggregates, admixtures that are used, as well as the mix design that we ultimately do in this particular environment. But what we usually do not control in a direct manner is the process of actually putting together the concrete structure, and this process involves the mixing, transportation, compaction, curing, temperature of the concrete, and finally the workmanship on the site. So, in other words, what we are trying to convey is what is there on paper does not always make it in the structure. You may always get perfect specimens, but the concrete inside the structure may not be of the same quality as we get in the specimens that are cast and cured in ideal conditions, because of all these factors that are actually affecting the properties of concrete over and above the actual materials that have been selected carefully by a proper mix design. Now, how do we address these? Using specifications. That is the primary challenge that we deal with as far as controlling concrete quality in actual construction is concerned. Okay. So, a specification typically tells you what? What is a job specification telling you? When you have a specification, let us say for the construction of a foundation for a building, okay, with respect to concrete, what does the specification tell you?
What has to be done and how it has to be done.
What has to be done and how it has to be done. That is in a more very general term, if you can be more specific. In terms of the methodologies and in terms of the guidelines to be followed, what do most specifications end up doing? It will mostly quote standards and code or codal requirements will be primarily used to convey the message that this has to be done in this particular manner. Okay. Now, the problem is the codes are only an enabling document. That means the builder can make use of the codes to build something when there is no prior information available on how to build it. The codes are not the end all. Okay. There are a lot of things, a lot of information is actually not there reflecting the codes, because codes are supposed to be understood at an equal level by all practicing engineers. But to incorporate some of the aspects that define concrete durability, it is probably not enough to actually just follow the codal requirements. Okay. We will discuss this in more detail later, because mostly what happens is there is no indication in the codes as to what durability test should I carry out to detect if my concrete is going to be durable or not. It just tells you, okay, here is a prescription, this concrete will be durable in this particular environment if you do all these things right. The problem often is that we do not end up doing all these things right. So, how do we address this in the specification to go and check whether the concrete quality in the structure is to the extent that we want and we had set on the paper itself. Okay, now let me give you an example. Let us say we talk about cover depth. Okay. So, the code says that for a particular service environment you have to have a certain cover depth, minimum cover depth. So, as per that, the specification tells you that you should use appropriate cover blocks to get that level of cover. Now, you use the cover blocks, but your process of compaction and vibration is not efficient and your formwork is not placed properly, because of which the cover blocks get dislodged and the actual cover that you get in the structure is much lesser than what you set out to have in the first place. Now, what do? You did as per the specifications, you followed the codes, but now you actually have a structure where the cover is not meeting the requirement. So, how can you tailor make the specification to address that requirement? What can you do? Exactly. So, there are methodologies for non-destructively measuring the extent of cover to reinforcing bars. So, why can't the specification say, okay, after the construction is done, show the measurement of cover on at least 5 or 10% of the locations selected randomly and see whether the cover is actually satisfying the requirements of the design. Okay. And that is where the specification actually can bring out these aspects which cannot be aptly covered by any codal recommendations. The codes can only tell you, okay, use at least so much cement, use maximum so much body cement ratio and so on. It can't tell you that, okay, after the concrete has been cast, do this test to determine whether the actual structure is matching the requirements of your design, and that only can be done with the help of the specification. So, a lot of the control of durability today is being brought about by the use of appropriate specifications. But the issue of specifications is a complex one. We will talk about that as we go along in this chapter. So, how do we specify for durability? One way is to simply prescribe or place restrictions on cement content, water to cement ratio, grade of concrete, cover and so on. So, cover here is a prescriptive requirement because the code says that I need to have so much cover in such an environment. It remains a prescriptive requirement unless you go back and check it in the structure and show that the actual cover is equal to your design cover, or at least it is equal to it with some standard deviation which is not too far from the actual cover. Okay. So, only when you measure it becomes a performance requirement. So, judging the compressive strength, shrinkage and durability properties required at a certain time period, these amount to performance specifications. Even measuring the cover after construction is done is actually an example of a performance specifications. So, specifying for durability can be done in both ways. The issue is whether we are able to completely tackle the problems that are associated with performance specifications. I will talk about that in some detail now. So, if you look at the Indian codes and specifications for concrete related structures, you have the IS 456 that looks at plain and reinforced concrete buildings. You have the Indian Railway Standard IRS 1997. You have the Road Bridges IRC code 112. You have several specifications from the Ministry of Road Transport and Highways as well as the guidelines for use of HPC, high performance concrete and bridges. You have metro rail specifications which are independently drafted for different cities where the metro rail work is being carried out, and then there is national highway 4-laning work which again comes up with its own specifications for the concrete. Mostly they are linked to the Indian Roads Congress because most of the concrete is being used in the bridges and the crossings and so on and so forth. mostly the structures are built with asphalt concrete, but wherever reinforced concrete is used, the IRC regulations are probably applying in those specifications. So, now we do not really have requirements for concrete set forth in a unified code in our country, and because of that there can be a lot of confusion. Now, just one point of confusion, for example, in IS 456 the maximum cement content is prescribed as 450 kilogram per cubic meter, maximum cement content. Why is that prescribed? From what perspective? Shrinkage and thermal stresses may be very high when you have too much cement present in your system. So, the code tells you that you should restrict your cement to 450, but the same maximum cement content requirement in IRC 112 is 540. No, it is not a misprint, it is 540, it is not 450 misprinted, it is 540, it is 540. And they say that in a bridge structure you can have as much as 540 cement. Sometimes the demands for strength gain are very high in bridge structures, and because of that the IRC is still permitting 540 kilograms of cement per cubic meter. But then the concept is still the same. If you have a higher cement content, it is obviously going to cause you greater potential for cracking due to thermal and shrinkage effects. So, why isn't the number the same? Why is there this difference? Where do you apply one or the other? Obviously, you will choose bridge structures, you will be applying IRC, but then does not the same logic apply that would fix the cement content automatically at 450? So, there is a lot of confusion, and especially when you start having these specifications that are made by the highway agencies and by the metro rail agencies, they tend to follow one or the other and it ends up in a lot of confusion. So, there is no clear understanding of why this is being done and why we should apply it in the first place. So, because of that there is a need for a unified code in the country. Unfortunately, that will be a dream all the time, because most of these codal committees are having their own stalwarts who have been heading these committees for years and years, decades. So, because of that we will not really see the unifying of all these codes, because of which there will still be some confusion in the minds of engineers. Nevertheless, proceeding forward, just looking at IS 456, if you look at durability and how it is addressed, there are generally 5 exposure environments as far as chloride exposure is concerned. You have mild, moderate, severe, very severe and extreme. Generally what we come across is limitations which are placed on minimum cement content, maximum water to cement ratio and minimum grade of concrete for different exposure conditions. Of course, this is an overkill, because if you really think about it, prescribing 2 of these should be enough, right. If you have water cement ratio, your strength is anyway automatically sort of fixed, right, and then you have cement content. There is no clear link between cement content and strength, but then in general for moderate levels of cement, if you increase the cement content, the strength also usually goes up at a fixed water content. So, then you have probably specifying all 3 of them is more of an overkill as far as the codes are concerned, but nevertheless we have it like that. Most international codes which use prescriptive specifications also specify all 3 values. There are limits on chloride and sulphate content of concrete. Of course, we do not want internal sources of chlorides and sulphates which will create problems from within. Nominal cover to concrete based on exposure condition is defined, and specific durability issues that are addressed include abrasive action, freezing and thawing, exposure to sulphate attack, alkali silica reactivity, presence of chlorides, concreting in seawater and aggressive soils. So, all these are addressed in one way or the other in the code, but there is no specific way of addressing them. There is just general requirements of the concrete which have been defined for these different durability problems. The inspection and testing is based entirely on compressive strength. There is no mention of conducting any durability related tests to actually ascertain the behavior in these different environments. And of course, they also talk about non-destructive testing to assess properties, including ultrasonic pulse velocity, rebound hammer, probe penetration, pull out and maturity tests. So, several tests are covered, but nothing points directly to the durability of the concrete. There are some examples from IS 456 have been captured in this table, and the remarks have been given in terms of trying to assess what is a shortcoming that needs to be addressed to make it a little bit better in tune with the current international regulations. IS 456, we know that last it was modified in 2000. 2000 implies that the information in IS 456 is possibly from 1995, because it takes a long time to actually write the codes, right. So, we are still working on information that was derived in 1995. The world over, especially in Europe, the EN 206, the codes for concrete, they have been rewritten and adopted by various countries as their national standards, and these are more recent and probably a lot more relevant with respect to concrete construction practice. So, there are a lot of remarks that have been put in the last column here, primarily looking at what are the shortcomings with the kind of durability treatments that have been done in IS 456 and what is the way forward. So, this is not something which we will discuss in detail, please read this on your own, and I just wanted to show you this table from IS 456 as far as chloride exposure conditions is concerned. So, we have 5 different exposure conditions for which the requirements of the water cement ratio, cement content and grade of concrete are given for 5 different environments here. So, let us just pick one, for example, the severe environment, and the description of the environment also is given in the codes. It tells you that severe environment basically is what type? Concrete which is made in the coastal environment. Now, what is coastal environment? There is no clear definition of that. Okay. So, we have to assume that it is something which is near the coast. How near? Again, it is left to interpretation. That is not a bad thing. We have to make sure that the engineer applies his or her mind to the situation to say whether the current project comes within the coastal zone or not. But very often it makes sense to actually put a guideline as to what should be considered as the end of the coastal zone. Okay. Now, CPWD has a nice regulation which says that anything which is 10 kilometers away from the coast or within 10 kilometers from the coast is considered coastal. So, let us say that we apply that environment here. The concrete can be designed for any grade that is required for the structure, but that grade should be fixed at a minimum of 30 megapascals, M30. That means, when we are in the severe environment, we cannot design concrete for buildings which is less than M30 if it is reinforced concrete. Now, you go out and see the kind of construction that is happening across the city, you will probably find only 10% of the projects actually have a strength greater than M25. Okay. Although we are in the severe environment in Chennai, most of Chennai comes within the coastal region, even if we take the 10-kilometer distance from the coast as a boundary, still only about 10% of the structures in the city are probably following this regulation strictly, because most builders do not really require strengths greater than 20-25 megapascals for the concrete, right. Concrete is simply sitting there filling the space. It is mostly the steel that they put in these structures which takes up the structural load. But unfortunately, because the concrete is not of the quality that is desired, you can lead to durability problems. So, when you are in the severe environment, M30 is the minimum that you need to have. Of course, once you decide that and you fix your water to cement ratio as less than 0.45, then the cement content requirement usually goes out of the window, because very few builders or very few concrete producers will actually produce this grade of concrete with as low a cement as 320. Now, there are practical implications. Let us say I am designing M30 concrete, okay, and I want to keep my cement content to the bare minimum prescribed by the code. Okay, so, I say I am using M30, I have a cement content of 320, I have a water cement ratio, I am maximizing it at 0.45. Okay. So, what is my water content? 0.45 multiplied by 320, that is, how much is that? 144, right. Now, at 144 kilogram per cubic meter of water, unless you use a very high range water reducer like a PCE based super plasticizer, you are not going to get any workability. If you add water, you would already disqualify the concrete from this requirement, right. So, you have to have a water reducer. Now, that means that you can't keep this level of cement in your system. So, you automatically have to up the cement content, probably you may go up to 380, right. When you go up to 380 at this water cement ratio, you will probably have enough water to work with a lower grade super plasticizer like an SNF, okay. Or even if you go for 400 cement, you probably will have enough water to not use any admixture, which is what is there in most specifications that is used in residential concrete construction, right. In those cases, people do not even use admixtures. Okay, when they are using RMC or ready mix concrete, obviously they are using concrete with admixtures, which is properly optimized with respect to cement content and so on. But people who are mixing on site, most of them are not using any admixtures. They may be using 400 kilogram per cubic meter of cement, which makes it 180 kilograms of water. Probably that is sufficient to give you the required workability, right. But then what are you doing? When you are changing a mix like that, you are probably not having an optimal concrete mix at all. For a grade of 30 megapascals, you have used 400 kilograms of cement, you're probably overshooting your cement requirement by several tens of kilograms of cement. So, what I am trying to say is this guideline is taken on a face value by the construction agencies. What you also need to understand is that the cement content is inclusive, is irrespective of the grade. So, whether it is 43 or 33 or 53, the same number applies and is inclusive of additions mentioned in clause 5.2 of the IS 456. Now, inclusions mentioned in 5.2 include slag, pozzolan, fly ash, metakaolin, ricer's cash. Okay. So, that means you can use any of these materials as a replacement for your cement and bring down the extent of cement actually that is being consumed in this project. Okay. So, you can actually make this 320 with 160 cement and 160 slag, that is perfectly allowed as per your codes. Okay. Only thing is, often people who do not believe in alternative materials start talking about this next line that is written. The additions such as fly ash or GGBS may be taken into account in the concrete composition with respect to cement content and water cement ratio if the suitability is established, and as long as the maximum amounts taken into account do not exceed the limits specified in their individual codes. That is okay. That means for fly ash we can't go more than 35%, for slag we can't go more than 70%. But then how do you establish suitability? What are the test methods with which you establish suitability? Nothing. As far as the code is concerned, it is only the strength and the workability. So, how do you establish suitability for durability in a severe environment with just the help of a prescriptive specification? You cannot. So, obviously, there is a need here to specify, okay, if you want to establish suitability, do this test and show that your value is coming within this limit, and then your concrete can be deemed to be suitable. Okay. So, that is what is lacking in the code. It does not really tell us as to how we can establish the suitability. It gives us a way forward for using mineral admixtures, but it does not clearly tell us how best to adjudge whether the concrete quality will be as good as the one with plain Portland cement. So, there is no mention of conducting durability tests to a certain quality, and acceptance criteria, as I said before, is just based on compressive strength. IRC 112 goes one step forward because it is meant to be the design guideline for concrete for bridges, where generally higher performance concretes are used, high performance concretes are used. So, here they do have a specification in terms of RCPT, water permeability and initial surface absorption test. They give values for what is acceptable, what is not. For example, if you look at RCPT, rapid chloride penetration test, the values specified in the IRC codes say that for a severe condition, your concrete should not exceed 1500 coulombs of charge that is passing through the system. Of course, we will discuss what this test is all about a little bit later. So, it gives you these values, but there are no guidelines as to how we can achieve these values. For example, if the code says or if the specification does not allow you the use of fly ash or slag or silica fume as a cement replacement, you can never get these good values unless you are overshooting on the strength requirement of the concrete. Now, I have told you about the example where fly ash was used not as a cement replacement, but as a fine aggregate replacement, because the contractor wanted to make use of fly ash to bring down the RCPT value to a controllable level, but they were not permitted to replace cement. So, they used it as an extra filler as part of the aggregate. Okay. So, there is no guideline given in IRC as to how we can achieve these values. RCPT may end up, as we discussed earlier, favoring mixes with silica fume or the ones which have reactive silica, which may not even be allowed in the project. In some cases, you may not be allowed to use these materials in the project. So, the specification has to anticipate this and address that carefully. So, that is how a performance specification should be drawn based on the requirements of the code and how well we can apply it to the given construction project. Now, metro specifications of course draw up different IS codes or the Ministry of Road Transport or railway specifications. Now, here they have actually called for durability testing also to be done, and when we were looking at Chennai Metro, the concretes that were designed for the metro had to pass not just strength and workability requirements, but also some minimum requirements with respect to durability tests. So, again they were looking mostly at the water penetration test, where water is penetrating the concrete after being applied under pressure, and then you determine the depth of penetration of the water into the concrete. Okay. So, the metro specs relied on some measurements being done on the actual concrete which was used for the construction project, and that brought about a slightly better control on the quality of the concrete that was supplied for the project. So, that way that is a step in the positive direction. However, even the metro project has not clearly linked as to what this value of 25 millimeters actually means as far as the service life of the concrete is concerned. Does this mean that my concrete will be durable for 50 years, 100 years, or what? They have not really used any models to bring that to light. So, again, what is the link to actual performance is something which is missing in this. So, critically what can be said is the specifications give reference to different standards to be followed, and they do not provide any information regarding the age of testing and the design life, and there is lack of clarity on limiting values of durability parameters as to how much is good, 1000 is good, 1500 is good, why is it good, how does it link to the actual service life, all that needs to be worked out in more detail. So, the lessons that were learned from a perusal of the Indian standards as well as the practices as far as concrete construction in the industry are: one is there is clearly a need to have guidelines and model specifications for construction projects in India regarding concrete durability, and this is something which is a work in progress. Actually, the Indian Concrete Institute has come up with a technical committee that works on identifying various aspects of concrete durability and finding the relevance of durability specifications in construction projects. So, that is something, that is a document which will be in the hands of all practicing engineers who are also ICI members. So, exposure classes need to be made more relevant. For example, we saw in the severe exposure class talks about corrosion, or it talks about chloride related corrosion, but there are several other types of durability problems that are actually missing. For example, carbonation related durability is not addressed in the Indian standard codes. So, deterioration mechanisms have to be accurately modeled using the exposure classifications, and that is something which is still missing. So, again, to recapitulate the approaches for durability design, you have the prescriptive approach, which can have two components: either avoidance of deterioration, that means for a project instead of regular reinforcing steel I specify stainless steel, right, because stainless steel will not corrode in the intended service life of the structure. So, I say that I choose a material that is not going to be deteriorating, so I avoid deterioration altogether, but we know that is not really a cost effective solution, right. Okay. So, we have deemed to satisfy approach where we say that if we use so much of this, so much of that, and do this mixing in this particular manner, assuming that we do everything on the field right, we will get durable concrete, and that is the kind of approach that is done in the current specifications, in the current codes, right, prescriptive specifications based on requirements of materials. The performance approach links to either the use of performance based tests and indicators, for example, the use of shrinkage test, rapid chloride test, water absorption test, and so on, to specify the quality of concrete in the structure, or through modeling. Supposing we have some inputs of the concrete available with us, can we use suitable models to establish what would be the service life of the concrete in this specific environment? So, there are models available, but the problem with models are there are several models available and no two researchers seem to agree on which is a better model to suit the durability requirements for concrete in a specific construction scenario or a service environment. So, models we still have not gained sufficient level of confidence with or agreement with as far as research is concerned. So, right now most efforts around the world are based on performance testing and using that to actually control the durability of concrete in the field. So, just again this is showing you the examples of performance and prescriptive specifications again. I am just not going to repeat that. So, the idea is that most of these are to be checked on the concrete that is supplied for the actual structure and not just established on concrete specimens that have been prepared using laboratory based mixes. So, when concrete is supplied to the structure, you either take concrete for testing directly from the structure or from specimens that have been subjected to exactly the same conditions that your structural concrete is subjected to. Because otherwise, when you are bringing specimens back to your lab, you are curing them in ideal conditions, you never know whether the results you are capturing are reflective of what is actually there in the structure or not. So, as far as possible, performance requirements should be tested on the concrete in the actual structure. How do we do that though? If you make a column, you want to test the durability of concrete in that column after 28 days. Can you go and start extracting a core from that column? If everything is all right with the strengths, nobody will allow you to touch the column to extract the core. So, what do? You may have to make specimens and cure them in exactly the same conditions, Alternatively, you can make mock-up structures which are standing in the same conditions, because in a cube you will never be able to simulate the effect of a reinforcement, right. So, if you make a mock-up structure where you actually have reinforcement in place also, then subject that mock-up structure to the same kind of curing that is being done in the actual structure, then you can draw your specimen from that and do the tests. And this indeed has been taken up by the South African National Roads Agency, SANRAL, and they are able to implement that kind of a specification on highway construction projects, especially for bridges where concrete is being used. They are actually mandating the contractor to put up concrete slabs which are basically mock-up structures which are subjected to the same kind of environment as the actual structure, and then specimens are drawn from that structure, measurements are done on those specimens with respect to durability indicators, and the numbers are compared with what is obtained from laboratory specimens, just to see the degree of control that the contractor has brought in for the concrete quality on site. Now, based on the difference from the lab controlled specimen, the contractor is either penalized for a poor quality or given a bonus for exceeding the level of quality that is expected in the field. Now, that is the way that we need to approach implementing the durability specifications. If there is no clarity in the spec as to what will happen if the numbers are not okay. So, I pull out a code from my concrete at 28 days and I realize that my durability requirement is not being met. So, there has to be some way forward. I can't just say, okay, not met, bring down the structure. That is not going to happen, right. I need to have directly in my specifications earlier that if the durability is low, first there is a penalty, financial penalty for the contractor. Second, there are remedial measures that have already been identified that need to be properly executed by the contractor on site. That probably is an extra cost for the contractor. So, from the beginning the contractor will know that the quality of concrete to be delivered in the structure has to meet a certain requirement. So, automatically the level of concrete construction will shoot up. Okay. So, this is how we see examples from North America where they use a lot of this rapid chloride penetration test, and they have specified it for bridges in certain states. For example, here the bridges, it says very clearly that the chloride permeability should be less than 1000 coulombs when you do not have a corrosion inhibitor in your concrete, and less than 1500 coulombs when you have a corrosion inhibitor in the concrete. Now, why does this distinction come about? The presence of a corrosion inhibitor may contribute some ionic species to your material which may end up increasing the conductivity. So, that effect is being captured in this issue of increasing the requirement for the concrete with a corrosion inhibitor. That means you are slackening the requirement for that. Okay. It also tells you that shrinkage should be less than 0.04% at 7 days for the superstructure and less than 0.05% for the substructure. Again, these are very clearly specified values that can be checked by the concrete supplier in the laboratory, get the mix pre-qualified to ensure that the concrete is accepted for the job, and once the concrete is supplied for the job, random sampling can be done and the same can be tested in the laboratory. Okay. Calgary City for high performance concrete uses RCPT as a requirement and says that your concrete should have less than 600 coulombs, but it tells you that if you are having 600 to 1200, you pay a cubic meter $40 per cubic meter penalty on it. Again, very clearly specified. Okay. It does not, all these things will not be there in any code, but the specification tells you clearly. So, specification is the main guideline which should be used for the construction, not the code. Again, Port Authority of New York and New Jersey uses RCPT for pre-qualification. It says that the concrete mix for pre-qualification should satisfy less than 1000 coulombs requirement, but the same concrete mix when it is supplied on the site where you expect greater variability, right, they allow up to 1500 coulombs in 80% of the tests. That means 20% of the tests can fail, no problem. Okay. So, that means they have built in some acceptance criteria for the concrete that is supplied to the job site. This pre-qualification criteria is the laboratory criteria based on which your concrete mix gets accepted for the job, but once it is accepted, it is supplied to the job, you expect that day to day there may be variabilities, because of that this allowance is given. So, there are distinct benefits when you use performance specifications. There is scope for innovation. For example, now there is nobody to tell you that you have to use 300 kilogram cement, you have to use 150 kilogram fly ash. No, you can use what you want provided you are meeting all these performance characteristics. Okay. So, there is possibilities of increased use of supplementary cementing material. So, obviously, we have some positive contribution we can expect towards sustainability. Client is obviously requiring a good final product, right. So, as long as you are getting good durability in the concrete, you are assuring the client of a good final product, and then people understand their roles in the process much better than if they are relying entirely on prescriptions. Of course, the main issues that we need to tackle as far as performance requirement is concerned is how do we define the mechanisms which are defining performance on a particular concrete construction project. So, this has to be agreed upon between the client and the concrete producer, or the client's PMC and the concrete producer before the concrete is supplied for the project, because only then if you arrive at a clear understanding of what should be the requirement of the concrete producer can then go ahead with the design of the concrete. Test methods to measure performance. Now, you will see later, based on the types of test methods available, people often are confused about what test methods are ideal to suit for a particular construction project. How do we make a selection of the test methods, and how to implement rules? That is the most important problem. What if performance is not met in the structure, and that has to be clearly written in the specification as to what are the penalties for non-conformance and what are the remedial measures to be taken to ensure that all this comes up to the level that is desired in the structure. The problem there is we are assuming that both the client and the contractor, or the client's PMC and the contractor, will have people who have sufficient knowledge of the material related issues and characteristics to be able to come up with all these requirements well in advance. But the truth of the matter is very few of our companies actually have a concrete technologist. Okay. Mostly they rely on the concrete suppliers to directly do the design. Concrete suppliers are not really interested in work durability. They only have to design the concrete to specify the strength and workability, so that it does not get rejected when it goes to the site. So, what does this tell you? All construction companies should invest in concrete technologists. Okay. So, there is a lot of scope. In fact, lot of companies look for concrete technologists because they do not really have anybody to solve their problems. The other issue that that is often bogging people down in the construction industry is that the clients have an automatic distrust of the contractor. They think the contractor is in the job only to make money. So, there are several projects in which I have been involved, in which I have been called as an expert to give an opinion on some problem or the other, which could be easily sorted out by the contractor's staff themselves. The third party is simply called because the client has no belief in what the contractor says. So, there are projects in which we have been approached to do concrete mix designs for M30 concrete, M40 concrete. I mean, these are some things that students can do sitting in the laboratory. Why do you need an IIT to come up with a design for M30 concrete? That is just because the client does not trust the contractor. The contractor has sufficient number of people who can do this design. The contractors know, they have been doing concreting for like years and years, right. For example, even L&T for instance. So, when you take up a job as a contractor, the client simply does not trust you to do the mix design yourself, and you have to approach IITs who would probably not be able to do the design because it is not suited in their best interest to be doing designs for run of the mill type jobs. We do not typically do mix designs for external producers unless the government themselves mandates that the design has to be done by IIT. Okay. So, what I was trying to say is several issues can be tackled by a better understanding of concrete technology, and if that understanding of concrete technology is there in the clients or the client's PMCs, they can certainly trust the decisions made by the contractor to select the kind of materials and mix designs required to put the concrete together for the project. Only in very specific cases we need to do additional investigations involving not just one lab, probably multiple labs, to ensure that we are getting the right quality of concrete for the project. But in most cases the contractors personnel, contractors laboratories are enough to carry out that kind of work that is required to produce the quality of concrete design. So, again these are issues that we need to overcome in our industry, work towards a much better harmony amongst people with respect to understanding material characteristics, and that is only possible if each side has a concrete technologist. Okay. So, I am just creating more jobs for you. Okay. So, we will introduce this subject today and continue this tomorrow. Primarily we will talk about transport mechanisms in concrete as to how aggressive agents are transported into the concrete, and how do we define these characteristics with the help of test methods? How do we ascertain these characteristics of concrete with the help of relevant test methods in the laboratory? So, I mean, of course, I do not want to scare you with equations at this stage, but the idea is that each of these mechanisms are usually quite well defined with the help of well known physics based equations. So, you have diffusion, which is one of the primary mechanisms, you have migration, permeability, sorption, convection and Wick action. So, all of these or a combination of these can act in any given surface environment to transport the external fluids into the concrete, which can lead to a deterioration of the concrete properties. Now, let us look at what happens when each of these acts on its own. Now, diffusion is a mechanism which defines the flow of ionic species under concentration gradient. For example, this is a barrier here, okay. You have higher concentration here and lesser concentration of the ions here. With time, the ionic species will tend to move across the barrier to the other side until there is some sort of an equilibrium attained in the concentration. Okay. So, if you can think of a semi permeable barrier, this sort of a diffusion will happen over time. Now, a steady state diffusion condition is one where this diffusion process is controlled by just the diffusion of the ionic species without a change in the properties of your material in which this diffusion is actually happening. So, gaseous diffusion in concrete happens in unsaturated condition, because if the concrete is saturated, if the pores are filled with water, gases cannot penetrate unless they dissolve completely in water. Most gases do not dissolve more than a certain extent in water, so they cannot penetrate if the concrete is saturated. Ionic diffusion generally happens through saturated and partially saturated concrete. For example, chlorides generally will tend to diffuse through saturated concrete, okay, whereas carbon dioxide will go through unsaturated concrete, which does not have moisture blocking all the porosity. Molecular diffusion can happen if the pores are relatively large. So, water penetration through the system will happen if the pores are relatively large to allow the molecules of water to penetrate the system. Okay. So, there are two equations of diffusion. One is the fixed first law of diffusion, which is steady state diffusion, and this second one is the fixed second law, which is non steady state. This is related to what I was telling about earlier. Diffusion happens in a material where the properties do not change with respect to time. Okay. When the properties of the material do not change with respect to time, I can apply the steady state diffusion characteristics. Here the flux is related to the diffusion coefficient and it is a function of the concentration gradient across the system. So, this is your material here, x is representing the depth in the material, right. C1 and C2 are the concentrations on the upstream and the downstream phases. So, a steady state condition is one where you will always have the same plot maintained for the diffusion process. That means the material characteristics are not changing with respect to time. So, the concentration has the same gradient with respect to depth throughout the life cycle of the material. Okay. Now, is concrete a material like that? Obviously not. We expect that with time concrete characteristics will undergo a change. Primarily, concrete will get more and more densified as the number of days progress. So, what will happen to this concentration gradient with respect to time? You may have a change in the gradient with respect to time. So, that means your concrete characteristics are changing, that means you can't be applying a steady state condition anymore. So, here this primarily applies to gaseous diffusion and diffusion across thin layers like membranes, like if you have a coating on the concrete surface for instance, you can apply the first law of diffusion. But if you are looking at diffusion through concrete as a material itself, you need to apply the second law, in which the concentration gradient with respect to time is written as a function of the diffusion coefficient and the concentration gradient with respect to the depth of the concrete. Okay. So, here with additional time your gradient is actually changing, because the characteristics of the material are going to be changing. Okay. So, here this equation does not have a direct solution, and it needs to be solved using a function called the error function. Okay. The other previous equation was a direct differential equation which can be solved directly, but here this is a second order differential equation, partial differential equation, which needs the error function for the solution. There are error function solutions available directly. So, I will talk about how this is actually applied to measurement of chloride diffusion in the next class. Thank you.